Hello everyone, and welcome back to Reverse Engineering Windows 32-bit applications. In this video, we're going to continue our discussion of heap buffer overflows. In particular, we're going to look a little deeper at some of our simple examples. So in a previous video, we had looked at this extremely simple program. I allocated 2 buffers, and then I foolishly copied user input into the first buffer, which had the possibility of overflowing a second buffer, which obviously could be bad. So I wanted to look at other ways that we could potentially abuse this little program and also look at a little bit more detail as to what things look like in this heap. All right, so let's go ahead and bring this guy up in our debugger again. So we're going to write EDB on our heap program, and we're going to start by giving it a few A's. Nothing that will crash it. So let me go ahead and step. And here we are in our user code in the appropriate segment. We can go ahead and do as we've done before and analyze this particular section. And let's go ahead and step a little further. Okay, so we're back here in our main method. For future purposes, I'm going to go ahead and add a breakpoint right here before our first malloc. And here we are getting ready to call malloc a second time. And we've called malloc, and it has returned a value, 09E98020. So that is a pointer to our second location. So let me go ahead and do this. Let me look at my memory regions. And I'll notice that here's my heap. Now, we've talked about this before, ASLR, how these things get randomized. So this is my heap this time, but not necessarily next time. So here we have our heap. If I look at this location, 09E98020, I will see that is the start of my second buffer, or at least the data for my second buffer. Now, before we kind of glossed over this, and I want to go back around to describing these 8 bytes immediately beforehand. And what are these for? So these bytes here are used to give my chunk size and my previous chunk size. So here I have my chunk size as 00000409. And you might say, well, that's a really odd size, Phil. And you would be right. So why do I have such an odd sized chunk? And here is the reason why. These chunk sizes will always be a multiple of 8. So what they do is they use the lowest 4 bits as status bits. So the actual size is 00000408. And that's giving us the 8 bytes for this extra bit of information. Previous chunk size is set at 0 in this case. So this is a pointer here. So what does that tell me? This is that internal structure that we were talking about. Now, as it turns out, there are different values stored at the beginning of a chunk if it's in use than if it's not in use. So we said this chunk size is 00408. So I want to go to 408 past this location. So if I go to add basically 400, I should go to 840. And I get to this location. So what is this? This is a chunk that has not been used just yet. So this is a pointer to its information. So this starts out with a previous chunk size, and then it's going to have this chunk size, and then it's going to have the buffer, and the buffer plus 1. So basically it's got a doubly linked list here. And that's what's going to be stored. Now, just to make this a little simpler, we will come back to this. So we will leave this the way it is for now. And we'll go back to the start of this particular chunk. And we will see what happens when we free this chunk a little bit later. And we're just going to run it normally first. I think this will make a little bit more sense if we do that. Okay. So let me go ahead and run my program. Here's my call to stir copy. And notice when I did that, I had my values in my first buffer. And now I'm getting ready to call free on my second buffer. So watch what happens when I do that. So notice once I called free, these values changed. And what did these values change to be? I have 4 bytes that are going to point to my next chunk, and 4 bytes that point to my previous chunk, chunk size, and previous chunk size. So now I have different values stored in here in these internal structures. Okay, so you might say, so what? Here's the key. If I overwrite this first buffer and I overwrite into a buffer that's being used, when I call free on that second buffer, it's going to look for my previous chunk size and my chunk size information. And it's going to use that information in order to free things up. So if I put a bad value into these locations, I can cause funny things to happen. What kind of funny things can happen? Well, I could cause it to actually crash, and we've seen that before. I can very easily crash the program because it will try to access some memory that's not accessible. And there are some other things that I could do as well. So that is a little bit more about this. Now let's go ahead and step forward some more, and we'll go to the second free and see what happens there. So I'm about to call my second free, and notice now that I've done that, it will change the first few bytes in my data. So the location of the chunk doesn't change. It's just what's stored at the beginning. So again, when I have an allocated chunk, the 8 bytes at the beginning of that chunk are used for storing previous chunk size and the current chunk size plus some status. Once I say, all right, I would like to deallocate that chunk, now it's going to change that information, and now it's going to change what's stored there. So I go from using 8 bytes to 12 bytes, essentially. Or depending on the implementation, 16 bytes. But in this case, it was just the 12. So now I have my previous chunk size, which is 0 in this case, this chunk size, so it's a pretty small chunk, 19 was the size, and the flags are set to, hey, this thing is available now. And this is executed and ended normally. All right, so that's just a little bit more detail about what happens. And again, here's how we cause the crash. If I go too far, so I'm going to overwrite this and say, let me actually get fancy here. I'm going to give it this Python. I'm going to give it a Python command. I'm going to say a times 16. I want to print 16a. So it's just going to overwrite this. So the null at the end is going to overwrite this buffer, but we will print that. Yeah, and we will start with that. So we'll just say, I want to just barely overwrite it. And we'll print this plus the string of B, 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 B. And I can verify if I go to this guy that I'm running it with these parameters, 16 A's and then 4 B's. So let me go ahead and run it to my breakpoint. And step it. Here's my first allocation. Notice that my stack is located here now on 0907. I can view. There's my heap. My first guy was allocated at 08. And here is my preamble. Here's my previous chunk size, and this is this chunk size, 1, 9. And again, it's really 1, 8. I have 8 bytes of overhead, and the 9 is a status bit, the extra bit, the 1. So let me go ahead and step forward. And we'll notice that our next chunk gets allocated. So if I started here and I went to 1, 8, the last 8 bytes here are being used. So let's go ahead and step. And now this is changed. And now this has a chunk size of 0409, which really means 0408 again. And we step through our program, and we'll see what happens. Here when we call our stir copy, notice that we overwrote this information. So everything is fine and dandy until we call free. And it says, I'm sorry, I cannot access that memory location. And I'm going to crash now. So what could I do in order to prevent this from being a problem? Let's say I wanted to run this program and I wanted to overwrite information in that second buffer without causing a crash on the free. Well, there's actually a couple of ways that you could do that. One way is to make sure that the buffer that you're overwriting will contain actual information that's valid. So it's going to contain an actual valid address. What would be a valid address? Well, I could put it somewhere on the stack. And that way it would be a valid address and I wouldn't get this kind of an error. So what's something on the stack? Well, something that starts with FFFB should be on the stack somewhere. So let me try that as a quick example. So we're going to change this. We're going to run it another time, but this time we're going to run it and we're going to give it an address that is valid. And remember, it's little endin, so it doesn't matter what you give it, these first couple. All right. And so now, once again, I'll run it to my breakpoint. Call my stir copy. Before I do that, let me go ahead and view my heap. I will step. And it looks like, let's see, am I right? Yes. I thought I might have been off by 1. But it looks like I'm okay here. So this is going to point to FFBF11A8, which might be on the stack. We'll see. So we'll step through this. And it looks like I wasn't quite on the stack. I was almost on the stack, but I should have chosen a different value here other than BF, something smaller. And again, the stack is going to be randomized. So sometimes you get lucky and sometimes you don't. So that is one way of making sure that this will be okay. I'll show you some other ways that you could make it so the program doesn't crash in some future videos. But that's pretty much what I wanted to talk about in this particular video. Now, as a reminder, this video is just one in a whole family of videos and courses that we have here at Pen Tester Academy, your source for everything InfoSec. And I look forward to seeing you in this course or another course soon. See you then.